So this is how a laser Doppler flow meter looks like. This is the monitor, this is the optical wire, and these are the detectors. Of course, at the skin also it is important having a stable temperature. Even you cover with a small cup, you have to keep this tissue stable, because you know, if you take a glove, after a while you feel warm, so because you cannot lose enough heat. So therefore it was technically difficult to maintain a stable temperature, but it is also done with Peltier, and so it is okay. So you stabilize it, and one provocation is always heating or cooling. So therefore, changing the temperature is changing the local microcirculation, and it could be one stimulus. And at the same time, what is also indicative for the skin microcirculation? Oxygen diffusion, because we are losing oxygen via our skin. The skin is not insulated for oxygen. It is a good insulator for anything, but the partial recurrent oxygen is changing because of the changes in the microcirculation. And one way of the provocation is, as I mentioned, you do a stimulus and look how the system is compressing. So I'd like to introduce you the so-called reactive hyperemia. Reactive hyperemia, which is easily performable. Having a cough, you close, like if there is a blood pressure measurement, close the circulation. This is the occlusion, and release the cuff, and this is the so-called post-occlusive reactive hyperemia. And what is it indicative, or what could be the indication? For example, how big is the compensation peak? How big is the area under this curve? Because normally, if you think, okay, we lost something during this time, which can be repaid or overpaid or not repaid. And if we look at the microcirculation of for example, diabetic patients, severe diabetic patients, there is almost no post-reactive hyperemia. So therefore, using laser Doppler photogrammetry was very important to figure out the microvascular changes in diabetic patients or kidney failure patients. Diabetes is also a very, very big challenge for mankind. I don't estimate, but now it is almost proven that around 10% of the population is diabetic. And diabetes is affecting the microcirculatory system in each organ. So the early detection and also the way of estimating the treatment effectivity is very important. So this is a laser, scanning laser image of the hand. And this is the normal microcirculatory pattern. Of course, it is color coded. You know, what does it mean? Color coding is always helping to having a better image. And where there is red, there is intense, there is blue, green, less intense, and it is the cuff. When we inflate the cuff, there is an occlusion, it is almost no blood flow. After a while, what do we feel? Pain. Why? Why do we feel pain? Why?
Because the volume and velocity of the blood coming back into our vessel and forcing new microcapillaries to appear, maybe?
It's no, just because the waste material accumulated because there's no transport is stimulating the sensory nerves, and of course after it there's a reactive hyperemia which disappears and it comes back to the normal stage. So these dynamics can be studied very well with the Doppler method, and as I mentioned, the area of interest is the dynamics can be analyzed. So this is a normal provocation again. This is a single point measurement before the stimulation or before the occlusion. It was normal flow. What can you also see in this report? Some dynamics. Flow is not stable. It is somehow changed. Why? Because our small blood vessels are doing something rhythmically, which is very typical for the entire body. So the cells are coupled and they are always talking to each other. There is always a dynamics, like very similar to the heart. So this in case of the blood vessels, it could be, this is called vasomotion. If you check a small vessel or a big vessel, the diameter is changing because of the pulse fluctuation, and also even there is no big pulse fluctuation because in the small vessels there is not too much pressure change. There is something which is called vasomotion, and this of course is the reactive hyperemia. Again, it was closed here. It was occluded, released back to normal, and start of heating. As I mentioned, heating is also a stimulus, and normally in the skin microcirculation, heating comes from 32 degrees centigrade to 42, because above 42 or above 44 it is painful. So, and you see here the dynamics for a new equilibrium. But what can you also see in this picture? The amplitude of the fluctuation is changing, and also somehow the rhythm is also changing. So therefore the temporal information can be also the frequency. The temporal information could be also the frequency. The temporal information can be drawn using, for example, the so-called Fourier transformation, which means that we are making a spectral analysis. As it turned out, that this spectral analysis is reflecting to the nature of the vascular smooth muscle cells, the nature of the innervation. The peripheral vessels are innervated mainly by sympathetic fibers. The loss of the sympathetic tone is resulting more and more fluctuation. So therefore, for an educated expert, this type of recording is conveying a lot of information. Again, back, what happened? We illuminated the skin with a laser light, and we are now at the level that we are talking about transmitters, nerves, and pathology or pathophysiology. So a few words about the brain. As I mentioned, in the brain, within few micrometers, there are many, many capillaries, as I mentioned, about 40 micrometers the distance, and the nerve cells are situated within this. And what is also important to notice in the brain. The skull is limiting the volume. So we cannot expand the volume of the blood by. Fluid is incompressible. So if you like to put more, you have to elevate the pressure to hell. And if the pressure is elevated to hell, they are compressing the vessels and there is no blood flow. Therefore, there is a fine regulation within them. The other issue is in the blood that the capillaries are funny. There is a so-called blood-brain barrier. Who studies physiology knows what does it mean? What is the blood-brain barrier?
From my best of knowledge, not every substance is able to cross this barrier, and very few substances are able to cross it, like alcohol, that's cross the blood-brain barrier, but there are some drugs which contain ingredients or say substances which can cross this blood-brain barrier. So
it's true. Actually, it was interestingly discovered. People are funny, really, so they do everything which is sometimes very strange. When the chemistry was booming at the end of the 19th century, new and new dyes were discovered. And scientists injected dyes to animals, with blue, reds, and when a certain dye was injected to the venous, intravenously to the rat, all the organs got blue, except the brain. What was the conclusion? The brain does not have any affinity to this dye. Okay, check other dye. The brain didn't get any affinity to other. Somehow the brain didn't like dyes. And the student of this professor, okay, let's inject this dye directly intracerebral. And somehow it turned out that the brain liked this dye. So therefore, the controversy was solved, okay, somehow it cannot penetrate through these capillaries because of the so-called blood-brain barrier. Which is on one hand good, because you eat something or drink something, if it is not alcohol, it cannot immediately reach the brain. The bad thing is that if you like to target a certain drug to the brain, you cannot do this. So it is also huge science. I don't go into details, just tell you that in case of the brain, there are funny things. So this is a superficial image of the brain. It's an animal's brain. This is a closed cranial window, which means that we open the skull, open the dura mater, the knee surface visible, closed it and filled the gap between the brain and the cover slip with artificial cerebrospinal fluid. And we investigated during years and years this type of structure because we checked the diameter changes, we checked the column changes, so we did a lot of stuff. But what is the limitation of having this type of program? You see only the surface. You cannot have any idea what is going inside the brain. So therefore, if you illuminate with a laser light, you can penetrate as deep as 1 millimeter or so. And so these are the major changes, the diameter changes. Actually, how is the resistance changing in a tube if the diameter is changing? What kind of equation is okay, so there is a tube. We don't change the length, only the diameter. It's a linear or sorry.
I didn't get the question.
Less the diameter, the resistance goes up.
Less the diameter, the resistance goes up. Higher the diameter, the resistance will fall. It's okay, but how?
I'm sorry, I didn't get the question.
Sorry?
I didn't get the question.
So it is a linear equation or square or
Square,
cubic.
because you have a surface
square.
in which the fluid flows.
It is changing on the fourth power. So it means that if there is 10% change, if it is a 10% change, it means that 10% higher, it means that the resistance is changing by 40%. Because 1.1 on the fourth power is about 142 or so. If it is downwards, it is also about 40% change. So therefore, small diameter changes are reflecting big resistance changes, and if the perfusion pressure is not changing, so the flow is so what are the major stimuli in studying the brain microcirculation? What is the easiest stuff you can change your brain microcirculation immediately? Yes? Okay. But you cannot repeat it too many times.
No. If you want to keep alive.
Sorry?
If you want to keep the patient alive.
Alive, you don't close the arteries. This is also. But how can you influence it easily and you start to change your breathing rhythm. You start to hyperventilate. And what is the result of it?
Too much oxygen. Increase velocity and blood pressure.
So if you go to the beach and try to blow a mattress up
Yeah.
or a beach ball, what do you feel if it's very intensive, this maneuver?
Bubbles. And you hit bubbles.
you are,
You also hear something in your hair. You also do
what is happening? You can easily faint. Why?
depression.
So what happens if you hyperventilate? One solution is you deliver more oxygen. But it cannot be okay because a lot of people inhale 100% oxygen and never fail. So it cannot be the way. What could be the other issue? You lose a lot of carbon dioxide. You wash out the carbon dioxide from your body. And interestingly, the carbon dioxide in the brain helps maintain open the blood vessels. If the carbon dioxide concentration is dropping, the blood vessels are getting narrow, and therefore less blood is going to the brain. It can be the opposite. If you give a little bit more carbon dioxide for inhalation, the brain gets more blood. So this stimulus is now showing that if you start with inhaling a little bit more carbon dioxide, in the normal air there is no carbon dioxide, 0.1%, this is not. But if you give 1–2% carbon dioxide in the Indian brain, the cerebral blood flow will change. It is a good test, checking if the regulatory mechanisms are intact.
What's if we use nitrogen, because sometimes it's a vasodilator as well.
Sorry?
What if we replace that with nitrogen instead of carbon dioxide?
No, in the air we have
I mean,
79% of nitrogen. It is not sensitive to this. So and also, as I have already mentioned, the laser Doppler flowmetry is a very good means to study rhythmic components of the microcirculation. So the other way is elevating the local blood flow is, for example, talking. Because some areas are activated. In rats, there is a funny model. You know, the rats cannot see well. Why? Because there was no need. They are nocturnal animals, they live in dark. But they can orient very well. By means of the whiskers. So they, in the narrow tubes, they sense everything. And somehow it turned out that if you rhythmically stimulate the whiskers, mustache, the brain is activated on the opposite side. Here, look, this is normal blood flow in a certain area. If there is a whisker deflection, rhythmically, it elevates immediately the local blood. This phenomenon is called neurovascular coupling. What is the mechanism behind? The neurons are sensing something, they getting activated, they use more glucose and oxygen, of course, therefore they need more blood. This is very important, again, because neurovascular coupling is telling now how the normal brain is processing the information. And the neurovascular coupling is mediated via chemical substances. It's a fast but it is mediated very effectively by chemical substances. And one chemical substance is the nitric oxide, which is converted from the amino acid arginine to citrulline. And if we block this enzyme, which is making this conversion, you look, this pattern, which was normally, is changing to this one. But can you notice, even knowing nothing about the physiology? And in this case, normally the local blood flow was at the level, it got elevated during the stimulation, it went back. If we inhibited one enzyme, this pattern is quite different. And even we did any other manipulation, we were not able to restore this. So again, I'd like to highlight laser Doppler flometry combined with the stimulation and combined with a little bit pharmacology showed something which was never ever discovered or observed before these methods. Why? Because of the temporal solution now enables us to see what are in the level of small microcirculation. So again, I'd like to explain. So this is the neurovascular coupling. If some neuron is active, it uses more ATP, requires more energy, oxygen, and the local blood flow is changing. This is a more complex figure. The neuron activity is elevated, the cerebral blood flow is elevated, and also the cerebral blood volume. How is it possible changing cerebral blood volume? I told you that this is a box which is limited in volume. Normally it is not changing, just the percentage of blood staying in the veins is replaced by blood staying in the arterioles. Actually, there is a fine interplay between the venous and the arterial part. Hemoglobin concentration. Hemoglobin is this is something which is carrying the blood. This is a protein carrying oxygen, and the hemoglobin absorption is changing depending on the oxygen saturation. We will see why it is also important. This is also an example how the local blood flow can be monitored by laser Doppler flometry. These are control circumstances. We did something. I wanted to show you that in the certain small region, the blood flow can change a lot during this type of stimulation. And now we are coming closer and closer to more and more sophisticated methods where we combine the laser method. This is the laser Doppler flow. This is the reflected light. This in various wavelengths, because the hemoglobin absorption is depending on wavelengths, and the dependence of the hemoglobin absorption is showing how much oxygen and how much carbon dioxide is in the hemoglobin. changing in this reason. And one good stimulus could be for the brain is the light. Repeated light to the eye will elevate the blood flow in the occipital cortex. So therefore, if we check here, we can see not only the blood volume but also the reflection of the different colors. And these are our studies. I'd like to really show you what are we doing here in the laboratory. So we try to do optical methods to study the red brain. This is a red brain. This is a laser flow meter. And also we check how can we visualize not only blood flow changes, but also the electrical changes. I mentioned that people are funny. They are using dyes for everything, even now. For example, some people are developing so-called voltage-sensitive dyes. What does it mean, voltage-sensitive dye?
What the electrical current changes in the gradient of the
If
electrical
the
current.
transmembrane potential is changing, they either absorb more or reflect more light. This is the way of. But the transmembrane potential in a living cell is about 70, 60 millivolts. Change in this range, the absorption or the reflection can be also changed, and so therefore we can visualize electrical changes even in a big grain surface. And this is a single point measurement. The electrical potential is change, which is also accompanied with change at the same point with local blood flow. Why? But what was the electrical change reflected? Neuronal activity. Neuronal activity is always something because neurons are fired. And local neuronal activity change was accompanied by an elevation of the local blood flow. What it is? It's a neurovascular coupling. Okay? Stimulate the whiskers, change in the local field potential because of active neurons accompanied with local blood flow change. How is it? Check. Checking the DC potential with the amplifier and looking at the local blood flow with a laser probe. I skip it because it means that we can destroy the system. Every system can be destroyed. The problem is that can we repair it? Because destroying is okay. Unfortunately, in the brain, not too much can be repaired. But new aspects, again, with optical methods. These are potential changes in a young rat. These are electrical changes, electroencephalography, and these are local cerebral blood flow changes assessed by laser performance. Every change is accompanied with a very nice. Why is it so interesting? Because after aging, the pattern is changing so. What can you see? Less peaks. So the old brain is quite different in this sense. And never ever was studied this type of change. Why? Because because we didn't have too much instruments and methods to study this. So therefore, if someone is interested, now it's a hot issue, the aging brain, the healthy aging, because the population is getting older and older, and the normal observations written in books are always on healthy 35 years old man. Now we have to fill this gap of healthy 85 years old woman. It is not easy to find healthy, or it is always a big question, what does it mean healthy? But this type of observations are made. So again, these measurements were made mainly by single point measurements. And now I'd like to a little bit talk about open field measurements, when the laser light is dispersed and we get back a scattered image. So these are skin microcirculation images. This is now this is the intensity, this is the perfusion, this is speed and concentration. So what can we deliver from this one? On one hand, the speed map, how quickly the blood is flowing, how much blood is concentrated, and also the dynamics of the perfusion. I put it how to, why is it important to check, but I tell you that we developed here in this building by means of my colleagues more and more sophisticated methods where we can simultaneously check many variables using laser diodes and LEDs, exciting the brain surface and getting back some images. So this is the time sequence, how we make a measurement. We illuminate sequentially the brain with laser diode, with LEDs, and we use two cameras checking or taking pictures and simultaneously collect these images and process them. So one issue, as I have already touched, is the hemoglobin. Hemoglobin is a funny stuff, because if you check the absorption of the light versus the wavelength, we can find that there is oxygenated hemoglobin, which is carrying oxygen. Actually, one hemoglobin molecule is carrying 4 oxygen molecules. And there is another form where there is no oxygen, and it is absorbing in this way. What can we use? If you use this wavelength where the both the oxygenated and the deoxygenated is absorbing at the same intensity, we can make a measurement which is independent of the hemoglobin concentration, the hemoglobin oxygen concentration. Therefore, it reflects to the local blood volume. Okay, because it is sensitive. This reflectance, because the oxygen oxygenated absorbs nothing. This reflectance is showing the deoxygenated. So therefore we can tell, okay, in this case the metabolism is high. Because if the oxygenated does not absorb anything, well, the only absorption is because of the deoxygenated, and if the reflection is small, it means that a lot was absorbed. Okay? And we can go up to the invisible spectrum where almost no absorption is. Everything is reflected, so we can use for blood flow measurements. So we used this principle and constructed a system, and like to finish up with this stuff. We use voltage sensitive dye, which is filled with this dye. This is the cranial window, and what is the funny thing? We can visualize electrical changes on the entire brain surface. We do some stimulus which results in change. And this is you can visualize how the electricity is moving through the brain of the rat, which was earlier only possible using needle electrodes, and